Hi guys, I think I said I wasn't going to do this example and for you to go over on your own, but I'm going to go ahead and do the example from the book. It's the example of the field inside of a long wire. It's example 28-6. Just so we have one solid example of Ampere's law to go on. I'm not sure I'm going to assign any homework on Ampere's law just because, like Gauss's law, there's so few problems that you can actually solve. So I'll have you look at one of the homework problems, suggest that you practice it, but I'm not even going to collect it. I'll show you what the answer is. Let me switch to just the document camera here. So Ampere's law says that if you integrate the magnetic field B around a closed loop, integral B dot dl, it's equal to mu zero, the magnetic permeability of free space, times the current through that loop. We can write through. And just like Gauss's law, it doesn't matter what path you take. This will always be true, but you have to choose a integral that you can actually do, which means you have to choose a path such that B is constant, or at least B is easy to understand and guess at the form of. And a path such that this dot product is preferably always 90 degrees. And you can actually use this to determine the magnetic field in certain situations. The example in the book says, imagine a wire of radius r carrying a total current I. What is the magnetic field at some point inside the wire? If we know that, let's say we put this in cylindrical coordinates just so that the symmetry of the situation is obvious. If this wire is essentially infinite in length, or at least very, very long, so we can ignore the end effects, we can put it in the xy plane like so. We should be able to tell from the symmetry of the situation that B can only be a function of r and not theta or z. So we know that at some point radius r away from the center, the magnetic field on that point anywhere on that circle should be constant. Again, just because of the symmetry of the situation. It could not be constant because the shape is constant and symmetrical with respect to the angle theta. So if we write the integral of B dot dl around this circle of radius r, we know that the magnetic field is going to be constant, so that's just B times the integral of dl, and that's equal to mu zero times the current through the loop. What's the current through the loop? It's the total current times the ratio of the surface area of the whole wire to the surface area enclosed by our little loop, which is pi r squared over pi r squared, where big R is the radius of the whole loop. So this is the current through our little Amperian circle that we have chosen here. The integral of dl around that loop is just 2 pi r, just the circumference of the circle. So we've got B times 2 pi r equals mu 0 I times r squared over the radius of the wire squared. One of those r's is going to cancel, and we get B equals mu 0 over 2 pi times, how do we want to write this? Just write I, well, let's see. We'll write I over r squared times r. We'll write it like that, so that it's clear that the magnetic field increases linearly as you go from the center of the wire to r equals r. And then once you get outside, it's just the same as the problem of just a wire. The whole current through the loop is just I, and it falls off like 1 over r. Again, this looks very similar to the example we did of the electric field inside of a cylinder. Instead of integrating over an area, we're integrating around a loop. But the fact that the field increases linearly as you go from the center to the edge Should be fairly straightforward. On your own, practice the homework problem that is a cylinder inside of another cylinder, like so. Let me check the homework really quickly, find out what homework problem that is. I know it's in here. That is problem. I can't find it. It's got to be in here. There it is. It's problem 31, a coaxial cable. And the way they have it set up in the book is a current I0 flows out this way, out of the page, and a total current I0 flows in the opposite direction in the outside part of the cable. So this is problem 31 in the textbook. I'll go ahead and I'll post this to the homework section, but I'll just post the answer right in the assignment. So there won't be anything for you to turn on. It'll just be a practice homework assignment just to see if you can get the answers, the formulas, and also the numbers that, that the book does. So I think that's all we'll do with Ampere's law. Like I said, it's an important law of physics, like Gauss's law is an important law of physics, but it is not particularly useful because there are not a whole lot of problems that, with our amount of vector calculus that we know in this course, where you can actually do that integral of the magnetic field around that loop, because we have to assume that B is constant and that B dot dl is always 90 degrees. It really limits the number of situations that have enough symmetry for us to actually be able to solve that problem. So we'll go ahead and leave it there for Ampere's law, and then I'm going to record a video about the law of Biot-Savart, and then we'll be done with chapter 28, I think it is.